model, the problem solving model, the structure that you use for solving these problems is very simple. And there are many more of these, and I'm going to throw some of them at you again next week as well as in the midterm. When you see a problem like this, you first figure out what is the structure for an optimal solution. Then you convert that structure into a recursive definition, and then you compute the value that you need using a bottom-up approach. So the recursive definition is important because it shows you what is going to be the equation that you'll use for using a bottom-up approach. If you were to generalize the lessons that you've learned from Fibonacci, you have to look at a second example. So what we've done is we looked at 3 specific problems. We've looked at a problem, and that problem was Fibonacci. Then from Fibonacci we went to factorial. From factorial we went to sum it all. And then we looked at a recursive definition, and then we looked at an iterative definition. Now I'm going to start off not with a recursive definition. I'm going to start off with an iterative definition, and I'm going to show you how even with an iterative definition I can write code which is horrible in terms of efficiency, and I can simplify that code to run much faster. There are a couple of sample problems that I've picked up from real life, and the reason why I picked them up is I want to give you a sense of how important efficiency becomes given both the context of the problem we're trying to solve as well as the amount of time it takes to solve it, and from the requirements from our clients in terms of how much time do we actually have to get back with an answer. Now, one of the requirements transferring money across borders is that you have to make sure that those transfers fit in with a compliance framework. So, for example, if you're transferring US dollars, if you're buying or selling US dollars generally settle in New York. So even when you write a check for US dollars in Pakistan, the actual record of that transaction goes to the US, goes to New York, and dollar movements happen in New York. If as an exporter I send money or I receive money and that money is in US dollars, that comes through New York. If I'm paying fees for my children or you're paying fees for your own graduate schools later on, that money will go to New York. And with respect to US dollar, there are specific requirements. So one of the key requirements is that you can't send money to people that have been sanctioned, that are on the sanction list. So if I'm a central bank, and this is a real example with a client that we worked with in Africa, central bank had about 8 million transactions that happened every day. And those 8 million transactions happened across 2 million accounts. And they had to meet these anti-money laundering, terror financing, and fraud detection requirements for those transactions. They had to do this in real time. So, when a transaction hits your system, you don't have end of day to find out, okay, this transaction will not be processed, or this transaction needs to be filtered out, or this transaction needs special processing, or this transaction needs to be sort of stopped, and this will not go through. And your primary operation is that for each transaction, you actually have 5 pieces. You have the person, and that person is the source who has sent the money. Then the person this money is going to, and that is the destination. So this is in terms of the counterparties, the party who sent and the party who's receiving. And these transfers generally happen through banks. So there is a sending bank, which is the bank that has sent the payment. So let's call this bank A. And then there is bank B, and that bank B is the destination bank. And then generally in between the 2 banks, between A and B, there is a third bank, and that is the correspondent bank, and that's called C bank. So remember, 8 million transactions. For all 8 million transactions, there are 5 names. There is source and destination, person who is sending, the person who's receiving, and then the 3 banks. And what you had to do for these 8 million transactions across these 2 million accounts is that you had to run these 5 checks on what? On a typical sanction list. And a sanction list is basically 50,000 names, roughly about 50,000 names. And there could be as many as 20 sanction lists. So that's almost about 1 million names. So for 8 million transactions every single day, you would take these 5 names. So this is 8 million, 5 names, and you would search them across these million names. And all of this is happening in real time, right? You can't do pre-work. You can't do pre-work because you don't know. So the lists, these sanction lists get updated every week, every 10 days, every month. and they are less of a problem. The bigger problem was these 8 million transactions. You would never know what was here, so you would search for them. And the response time in which you have to find out whether a transaction hits a match and a certain action has to be taken with certain information. There's certain forms that need to be generated when a suspicious transaction is identified and declined, or when a transaction is approved. In both instances, so the search, the paperwork, the generation, all of this is automated, and all of this had to be done within 120 to 180 seconds. That's the response time, which that then gives you a sense of why writing efficient code is important. So if you're not done this well, if you've not done this correctly, if you're not doing this the right way, you will run into trouble. A lot of times that you'll only find out that you've run into trouble when the code hits your customer's production site and the production site comes to a problem. And that's happened to me multiple times, not just one, multiple times. It happens because, we don't understand how efficiency is done, which is the reason why we're emphasizing spending so much time on making sure that you understand efficiency in your first 6 weeks at IBA. And then you can put this to practice in order to build this as a habit, as part of not just your work routine, but also as part of your review process for the code that you write. A second problem, matrix multiplication. We wrote a risk management software that was essentially meant for investment, treasury, and portfolio management teams. And here, our challenge was to calculate the risk inherent in a portfolio with about 10,000 positions, which then led us to a different challenge. And that challenge was, remember these words, this is called portfolio volatility. The standard deviation of the portfolio. The standard deviation of the portfolio was basically the standard deviation of all 10,000 positions plus the correlation between these 10,000 positions. And this is a fairly awkward calculation process that took a fair bit of time. Later on in the course, when we come back to efficiency one last time, when we come back to market practices and areas of expertise that you can specialize and focus on, we'll talk about this example. So that's 2. The standard deviation of a portfolio is essentially 2 positions, A and B, with weights A and B. And as you go from A and B to C, the positions increase and the weights increase. So think in terms of the easiest way to look at this. If you remember, you've done the word generation combination. So word generation was, let's say, A, B, C, D, and E. And then what did you do? Then you mixed and matched these. So now think in terms of, this is my position. This is my weight of that position. WA, WB, WC, WD, WE. And then this is my A, B, C, D. And this is A, B, C, D. And this is my correlation or covariance between these positions. So I had to essentially do this and then do this. Multiply these 3 matrices together. So if you have 10,000 positions and you have 10,000 weights, then this matrix, this one, the correlation one, was basically a matrix by 10,000 by 10,000 matrix. As I said, the calculation got fairly involved, fairly fast, fairly quickly. Once again, there was a need for you to figure out how to do this efficiently. And we'll talk about this not today, but later on in this course. Right. This you've already done, which is the Android map application problem. This we did on day 1. If you have a billion devices, you need to track time, you need to track where they are, track location, figure out the shortest point between distances. Once again, the response time that's required and the response time that's actually implemented is quite unreal. So there's a lot of thought that's gone into solving these problems in an efficient fashion. One of the problems, the problem that we're going to talk about next, is the fraud and anomaly detection problem. So again, banking example, if my card gets hacked, if my account gets hacked, if my application gets hacked, and I want to get a sense of How do I know what the baseline number is? What I really want to do is I want to get a sense of what my average account balances are like, what my daily transactions are like. So what is the easiest way of detecting something is wrong, or something is missing, or something is a problem, or your account has been hacked? So there is this baseline. This is what my baseline looks like, and this has been my average for the last 10 months. So for example, when I go to the ATM, on average I draw 10,000 rupees from the ATM. What if I suddenly start drawing 500,000 rupees from the ATM every day? That indicates as a challenge. Similarly, in terms of amount that comes into my account, let's say, I get my salary and I get some other payments, so the total amount comes into my account is X. What if I suddenly start getting 100X amount into my account? So that is again, so how do you find out that there is something that is happening, which is an exception, and that exception needs to be tracked? You do that by figuring out what the averages are on a day-by-day basis, and then you track those, and then you plot those, and then the ones where there are exceptions happening compared to the averages, those are the ones that you follow through. So this becomes what we call the prefix average problem. The prefix average problem is this problem. If I give you 10 numbers or 15 numbers or 20 numbers or 30 numbers, what I want you to do is I want you to calculate the average of the first numbers. Think of this as, this is the first day, second day, third day, fourth day, fifth day, sixth day. I'm calculating, let's say, monthly averages every single day. So I'm calculating averages for every day for the month, and I'm repeating this every month for every month in the year. So for example, the average of the first day is going to be the first price. Average for the second day is going to be the first and second price. Average for the third day is going to be the first, second, and third. Fourth is going to be first, second, third, and fourth. Fifth is going to be first, second, third, fourth, and fifth, and so on and so forth, right? So we call this the prefix average problem. And when we come back from the break, the prefix average problem is the problem that we're going to try and solve. The way that I've structured this is, rather than giving you something boring such as my bank account balance, I am going to give you the share price of Google for about 18 days. And what I want you to do is calculate the prefix average for this, then for this and this, then for this and this, then for this and this, and then so on and so forth, right? And this process is called the prefix average process. So when you come back, we will first write code that we think is the easiest, the simplest, the cleanest way of writing it, and then we'll figure out how to make that code more efficient.